In this practice problem, we are given information about a reaction. It reads, the following table shows the rate constants for the rearrangement of methyl isonitrile at various temperatures. The K constant is given to us in per seconds, making this a first order rate law, and the temperature is given to us in a degree Celsius. We are being asked to calculate the activation energy for the reaction. The activation energy can be found by using the Arrhenius equation. I like to use the non-graphing Arrhenius equation. It saves me from generating lists in my calculator. To remind us, we just wrote that up above. Let me scoot that down and write that with us again. Where the natural log of the rate constant K1 over rate constant K2 is set equal to the activation energy over R, the ideal gas constant, times the difference between the reciprocal of T2 and T1. When we take a look at the non-graphing form of the Arrhenius equation and we look down at the temperature, I notice that the temperature must be in a Kelvin unit, although they've given me the degree Celsius. I'm going to keep that in mind before I plug in a value to be sure that these are always in Kelvin units. What I also think is best, knowing that activation energy truly represents the slope of the line, I suggest taking the farthest points possible from this list to get a better measurement of the slope of the line. So let's call our first value from trial 1, and the next value we'll use comes from trial 4 down below. So we're going to compare the first line and the last line of our data table as we calculate the EA, the activation energy for our reaction. So let's plug in. Here's what we know. That the natural log of the ratio of K1 over K2, K1 is given to us as 2.52 times 10 to the negative fifth per seconds. And I'm going to put that over K2, grabbed from the last line of the data table, 3.16 times 10 to the negative 3. Again, the reason, since we're solving for slope of the line, we want the longest line possible to get a best representation of that slope. The ratio of K1 over K2, set in front of the natural log, is now found by taking EA over R. R is our constant, 8.31 from the gas laws chapter, times the reciprocal of T2 minus T1. We've got to convert those Kelvin temperatures. 251.2 plus 273 is showing me a first temperature reading of 524.1, just adding that in there, 524.1, and that's Kelvin. I'll do the same thing for that original temperature, 189.7, adding 273 to find the Kelvin temperature, and we get 462.7 for the second temperature. Let's simplify this equation, pulling out for EA. I'm going to just take this paper off and kind of share what I did for the algebra problem. Again, this is nothing more than the recopied of what we've just wrote on our note pack, where the ratio of K1 over K2 is equal to EA, set over 8.31, our gas constant, and inside this parenthesis is T2 minus T1, just converting those into a Kelvin unit. Notice that K1 over K2 is on the left, but T2 minus T1 comes from the right. You want to be sure that the temperature value for K1 is going in the second temperature reading over here. Now when we simplify, the first thing I did, maybe I'll cover this part, is just simplified the ratio, the natural log of 2.52 e negative 5 divided by 3.16 e negative 3. When I just hit that out on my calculator, I found negative 4.83945. I then simplified what was inside the parentheses here for the differences in those temperatures. Taking the reciprocal of T2 minus T1, that simplified to be negative 2.5355 e negative 4. Having accomplished the parentheses simplifying, we're trying to isolate EA. Then what I did was to divide both sides by the 2.5355 e negative 4. I'm trying to cancel out to isolate EA. So then on my calculator, I simplified the left side. I took the negative 4.83945 divided by 2.5355. And now what I show is 19086.1 is equal to EA over 8.31. Simplifying the left is our next step in isolating the activation energy. To get rid of the 8.31, what I did next was to multiply that by both sides, so this then canceled, and now finally we have our answer to the activation energy. When I hit the R constant times 19086.1, my calculator read 15,865.56, very large number, 158,605 joules. So then I just converted that to a kilojoule by dividing by 1,000. Our activation energy, our target variable, EA, once solved for, came out to be 158.6 kilojoules of energy.